This is Neil from Anemometer, and in this tutorial, we're going to cover how to measure wind speed from a pulsed output anemometer. And this is going to be a standalone tutorial on measuring wind speed with an anemometer, but it's also going to be part of a larger series that Anemometer is going to do on building a portable IoT weather station that can measure wind, temperature, humidity, pressure, moisture, ultraviolet rays, all kinds of things. So if you're interested in that, please subscribe to our YouTube channel and you'll know when those other videos start to come out. If you're not familiar with Anemometer, check out anemometer.co where you can see our open source data converter products, ADCs and DACs, as well as some of our IoT boards. All right, so there's various anemometer types out there. There's pulsed output, there's analog output, and there's digital communication output. We're just going to cover measuring pulsed output anemometers, which are the most common. Now, there's a couple different architectures for pulsed output anemometers. One of the more common ones is the ones that have a transistor or MOSFET solid-state switch that switches on and off as it spins. And the idea is it creates a pulsed output. That's why they're called pulsed output anemometers. And you basically count the edges of the pulse and the timing between them to get the wind speed. And we'll go over that in more detail, obviously, in the video. There's also the mechanical switch version. The mechanical switch version, you have to provide your power to it and you measure the power on the other end based on the mechanical switch. And I'm saying power, I should say voltage. So I've worked with both mechanical and transistor-based. They also have optoencoder-based and Hall effect sensor-based, which I think are a little more rarer. Once again, you apply a power supply and you're going to get a pulsed output. Okay, so let's talk about the hardware setup in a little more detail. Then we're going to look at a demo of an anemometer in action and us making measurements. Then we'll dig into the software. So there's two aspects of this tutorial, the hardware setup and the software. And of course, I'll provide a link to GitHub where you can access the software that I go over in this video. Okay, here's sort of a blurry picture of the architecture of an anemometer. In fact, it's the model number that I have up there. This is the anemometer I'm going to use for my demo. The dotted lines represents the internal part of the anemometer. So this MOSFET or transistor-based one has a control circuit. So you apply a power supply. The control circuit then turns mechanical motion into controlling this gate of this transistor, basically turning it on and off. And on means the transistor acts like a short or a closed switch, and off means the transistor acts like an open or an open switch. And this is an NPN-based setup. So the idea is the power is on the high side and we measure in the middle, and this is sort of a low side transistor, right? They also make PNPs. So if you're familiar with a PNP transistor, that's more of a high side switch device. And so that would be up here, and then you would just move this load and everything down here, right? But I prefer to work with low side, so that's why I went with an NPN anemometer. And the way this works is we power the control circuit, and then we use a load or pull-up resistor, pull this voltage level up here. They're using the word current, which I don't like that, but the idea is when the transistor is off, we should get a voltage drop here, and we can measure that with our microcontroller using a digital pin. Or when it's on, basically this pull-up resistor will no longer have a voltage here because this is going to act like a short. So then we have a low level. So we can get that digital pulsed output based on how fast the anemometer is spinning. Now here's the exact setup that I'm going to use based on the microcontroller I'm using. So I'm using Anemometer's AIoT Sense node. This will work though with any microcontroller. The AIoT Sense node has a 5-volt power supply. So that's what I'm using to power the anemometer. My ESP32 can only work with 3.3 volt logic. So I didn't want to do a pull up to this power supply. Instead, I'm going to use my other power supply on this board, 3.3 volts. If you're working with a microcontroller that's 5-volt tolerant, you could just use this power supply. So the idea is I'm powering the control circuit, and then I have 3.3 volts and a pull-up resistor, and then I'm connecting to my microcontroller pin. Now, the reason I have the word int or X, internal or external, by the pull-up is the ESP32 actually has an option where if you can set its digital input pin to measure a digital input, and you can set it with a pull-up resistor. So it's pulling it up to its internal power supply, which is 3.3 volts. So I don't even need this resistor. Now, if you're working with a microcontroller that doesn't have internal pull-ups, you would need to add this resistor. So all this setup is just 3 wires to my microcontroller, really simple. Now, one thing I wanted to show you real quick is just a mechanical anemometer. So one thing you have to be aware of with mechanical anemometers is switch bounce. So if you're not familiar with mechanical switch bounce, it's the idea is when the mechanical switch closes real quick, it actually doesn't just make a contact and stop. It'll actually bounce a little on that contact. And that's bad because instead of creating a nice clean pulse, it creates multiple rise and fall times or multiple tiny pulses that can cause your microcontroller to misread and make inaccurate wind measurements. Now, there is ways to deal with switch bounce in software, but it's so much harder and it slows down your software. I prefer to deal with it in hardware. So this basically plus V represents the power supply you're applying to your mechanical anemometer, and this represents the switch inside your anemometer that's opened and closed based on how fast the anemometer is spinning. So this debounce circuit takes this value, and first of all, we have a diode, which just allows positive voltage to pass. Then we have some resistors and a capacitor that basically create an RC network where the capacitor has to be charged and discharged. Well, the idea is the capacitor will not charge or discharge real quick. It'll charge or discharge based on an RC time constant. So that RC time constant basically smooths out those jumping around caused by the switch bounce. So it gets rid of it. Depending on your setup, you may need to adjust these resistor and capacitor values. Based on this RC time constant, instead of getting a nice, clean, sharp pulse, you get more of a rounded hump. And you could measure that with your microcontroller, but I like to add a Schmidt trigger. It basically has a very accurate trigger level and turns that hump into a nice, sharp pulse to measure the rise and fall time. And that's what we're going to do in software, is we're going to trigger off the rise and fall time of the pulse. You could get away with just a resistor and a capacitor in the most simplest form. I prefer this whole setup though, so I get nice, predictable, sharp rise and fall time pulses. So this is how you would deal with a mechanical anemometer. And then lastly, I wanted to show you the output of an anemometer. So this is the one that I'm going to use for the demo that we're going to look at next. But basically, I connected an oscilloscope to the output pin that's being pulled up to 3.3 volts to measure the pulse. And of course, I spinned it with my hand to create these pulses. So the idea is if the wind was not blowing, we would just see a DC level pulled up to about 3.3 volts because of the internal pull-up resistor of the ESP32. So I spun this and we can kind of see these pulses. And one thing I want to point out is we have amplitude on the x-axis and time on the y-axis. So you can see this grid right here, and we can see our pulse fits in the grid and is a little bit smaller than this grid, right? So we can see the pulse on the inside of these grid lines. But if we go over here to the right, we can actually see the pulse perfectly fits and lines up with the grid lines. And that's because the pulse size is changing as the anemometer slows down. When the anemometer is going fast, the MOSFET switch or the mechanical switch is turning on and off quickly. And as the wind slows down, these pulses get longer. And for our demo and for the software I'm going to use, we're going to trigger off the fall time of the pulses to measure the wind speed. Okay, before we dig into the software, let's see this in action. So this is the exact model number of the anemometer that I showed for the example schematic diagram. And we have Anebit's AIoT sense node, and we have a solar panel and a battery. So we're outside, we're running off of battery and or solar panel, or solar power, I should say. Then we have my phone, which is going to connect over Bluetooth to get the wind data from the ESP32, which is getting it from the anemometer. Check out the AIoT Sense node on anebit.co. It has a lot of great features. As you can see, it's real power flexible. It also has a USB-C connector. You can power off that. You can program the ESP32. Has a lot of measurement features for monitoring the battery. It also has a really accurate ADC for making external analog measurements, which the ESP32 is not good at. So anyway, check it out. But you can see I have some natural wind right now that's just blowing around in my yard in Grand Junction, Colorado. And we're going to zoom in here. We can see our battery is connected here, but this blue wire is the measurement point. So this is connecting to pin 11 on the ESP32. Then our brown wire is connected to 5-volt power supply, and our black wire is connected to ground. And this yellow wire is not used. So I have a little bit of wind spinning, and I'm going to basically send a character over Bluetooth to the ESP32 to collect some wind data. So the idea is the ESP32 is continuously measuring wind data, but it only sends it out when you request it. And the way this software is set up is you can either request data over a serial monitor connection if you have your laptop computer, or you can use a UART to BLE or BLE to UART app like the one I'm using here. So I sent a character. It sent me the latest wind data. The pulses for instant measurement are based on a 1 second interval, as we'll see in the software, and then average wind speed over 60 seconds, then gusts. Gusts are measured over a 3 second averaging time in this moving 60-second window. And this is all in the software. And I didn't just make up these wind measurements. These are actually standards for how you measure wind. So instantaneous, we have no wind, but you can see the wind was blowing a little bit over the average and the gust in the last 60 seconds. So we get a little more action. What I'm going to do is I'm going to spin it myself, kind of simulate a big wind gust or some continuous wind, and then I'm going to request some more data. So now we can see a little more action here. We can see that we actually got some pulses in the last second, right? So this instant and pulses in the last sample represents only 1 second. So we can see in 1 second, we got 11 pulses, which is doing more than half a revolution, right? Because 20 pulses is a full revolution. If you have 20 pulses in 1 second, that's one full revolution. That equals 1.75 meters per second. We're getting just under 1 meter per second, which makes sense because we're a little higher than, halfway being 10 and full revolution being 20. And then, of course, we have some other pulse counts in between there over the last 60 seconds. And of course, when I first spun it, in that 3 second window, we got 8 miles per hour. So that was the highest gust we got. So we can see we went over the hardware and we can kind of see the demo in action. Now that we understand what the measurements are, let's look at the software to see how they're being done. Okay, we're looking at my anemometer wind measurement over BLE. This is an Arduino sketch. I'll post it on GitHub. I also have a version that doesn't have Bluetooth. It just has the serial monitor code. So I'll post that as well if you're not interested in Bluetooth. But I have some notes here. Basically, for my model, 20 pulses, 1 complete anemometer rotation. 1 complete rotation per second is 1.75 meters per second. And I do this all in constants, so you can adjust this to whatever anemometer you're using. I then explain my wind measurements. Instant is over the last second. Average is over a 60-second window, but you could change that if you want. And gusts are in a 3-second average observed over this average moving window. And then, of course, the serial behavior is it only prints data when you ask for it. All right, I'm not going to cover the Bluetooth code. Let's get into some of these constants. So this is my anemometer pin that I'm using on the ESP32. My sample interval, my minimum sample interval for instantaneous wind is 1,000 milliseconds or 1 second. My average second window is 60 seconds. Of course, you could change that to be 2 minutes, 5 minutes, 10 minutes. My gust average seconds, which once again is based on a standard, is 3 seconds, and that's moving over an average window of 60 seconds. Pulses per cycle, 20, and I got that from the data sheet. So if you're using a different anemometer, you'll probably need to change that. And meters per second per cycle, and then, of course, a conversion factor to miles per hour from meters per second. And then this is going to be an interrupt-based measurement. So the idea is whenever that pin detects a falling edge, it calls an interrupt function where it's going to up this pulse count. So we keep track of the pulse. And then we have some timing variables that we'll see in action. And then for our averaging, we're going to keep a history for every second we gather measurement data, and we're going to store that in an array. And this, is a moving window. We average it together to get the average wind speed over a certain period of time. And then, of course, similar with gusts. And then we have some global variables for storing this information, these different measurements in meters per second and miles per hour. Here is our ISR, or interrupt service routine, which is called every time a falling edge is detected. So we up the pulse count, and then we use a timer in our main loop to do our calculations, right? We don't want to pull and look for pulses over and over and tie up our ESP32 from doing other stuff. So we're using this simple interrupt service routine to do that. All right, in the setup, we're setting up a lot of our communication, including our serial monitor and our Bluetooth. Oh, I should mention, here's where we set up our pin. So we have our input pull-up. So that is what adds the internal pull-up resistor, and we're specifying the anemometer pin. We then do digital pin to interrupt. These are all Arduino built-in functions. We attach an interrupt. This is our interrupt service routine, count pulse, and then we want to trigger off the falling edge. And then the last thing we do in the setup code is we get the current millisecond timer value because we're going to use that in our main loop to do our calculations. And then speaking of that, we grab the latest time and we compare it to our sample interval in milliseconds, which is 1,000 or 1 second. We do that, and if that's true, we are ready to do a instantaneous wind calculation as well as store that data for doing average calculations as well. So we grab some timing variables and store them. Then we briefly shut off the interrupts, right? Because we don't want any pulses happening while we're doing this short calculation. We grab the pulse count and then we reset the variable to 0, and then we turn interrupts back on. Remember, this happens in like nanoseconds, right? So chances are there's not going to be a pulse in here. And anyway, it doesn't matter. We're keeping track of the timing variables anyway. We then take our pulses and we put them in the latest pulses because that's what we use for our average calculations and things like that. We convert elapsed time from milliseconds into seconds. And since we're using a float, we can handle fractional seconds as well. And then here's where we're doing our instantaneous wind calculation. And this is all based on the timing, the 20 pulses for a full rotation, and that 1.75 meters per second. So first of all, we determine how many pulses happened in that second. Then we turn that into pulses per second. Then we use our meters per second and the number of pulses in this time period to get the instantaneous meters per second of the wind speed. So that's how we're calculating the wind speed. And then we use this fudge factor right here to convert it to miles per hour. Then we start storing these pulse counts in our array that does our average calculations, right? And we check our index variable. We also check if the array is not full yet, if the program just started. And then we do some calculation of pulses. And then we're able to get average pulses, over the last 60 seconds or whatever you set it to. And then we're able to get gust pulses or gust calculations from the pulses. So that's the software. I will post this on GitHub and provide links to both versions of the software. Okay, that's it for how to measure wind speed from a pulsed output anemometer. If you have any questions from the hardware or the software, please use the comment section in the videos. And if there's anything I missed and you want to add, please add that as well. Keep in mind, this is going to be part 1 in a long series for building a IoT weather station. If you haven't already, check out anabit.co where you can find our AIoT Sense node, which was used in this video demonstration. And if you like what you see here, please hit the thumbs up. Thank you for watching.